Dear students, today let us explain the chemistry paper 6 of 5th semester BSc chemistry syllabus of Kuvempu University, in which we are having a discussion on session 35, which is the part of the chapter 1 in the inorganic chemistry, that is coordination chemistry, in which we are going to discuss about the stability of complex compounds, in which we are having a discussion on stepwise stability constant and overall formation constant and factors influencing the stability of complexes, particularly the nature of metal ion, nature of ligand, and chelation effect and macrocyclic effects. In our previous session, we had discussion on the types of isomerism, that is structural isomerism, in which we had discussed on the linkage isomerism and coordinate isomerism, and in the geometrical isomerism, that is optical and geometrical isomerism in complex compounds with coordination number 4 and 6. The objectives of the present session is to understand the stability of complex compounds and to get a formula for stepwise stability constant and overall formation constant, and to understand the factors influencing the stability of complexes, particularly nature of metal ion, nature of ligands, chelation effect, and macrocyclic effects. The outcome of the present session, one can understand the stability of the complex compounds, and also we can learn how to get the effect, how to understand the factors influencing the stability of complexes. Let us see what is meant by the stability of complex compounds, and we should know the stability constant for the formation of a complex compound. A stability constant or formation constant, or also called as binding constant, is an equilibrium constant for the formation of a complex in the solution. It is a measure of the strength of the interaction between the reagents that come together to form the complex, and it provides the information required to calculate the concentrations of the complexes in the solution. There are many areas of application in chemistry, biology, and medicine with respect to the stability constant of the complex compounds. In studying the complexes, that is formation of the complexes in solution, there are two types of stability of the complexes. One is called as thermodynamic stability and the other one is called as kinetic stability. Now let us see what is stepwise and overall formation constants. According to Jerome, the formation of complex MLN in the solution proceeds by the stepwise addition of the ligands to the metal ion. Here M is the metal ion, L is the monodentate ligand, and N is the maximum number of coordination number of the metal ion M with the ligand. In the first case, there is only addition of one ligand to the metal ion, that is M plus L, in equilibrium with Ml. So the equilibrium constant here, it is given by the concentration of product divided by the product of concentration of reactants, that is Ml divided by M into L. In the second case, one more ligand is added to this Ml formed in the first step, that is Ml plus L gives Ml2, so therefore equilibrium constant K2 becomes Ml2 divided by Ml into L. Similarly, in the third step, Ml2, which is formed in the second step, is added to one more ligand, that is Ml2 plus L gives Ml3. So the equilibrium constant K3 becomes equal to Ml3 divided by Ml2 into L. Similarly, this process continues to get the total number of ligands added. Here is MLN. So here one ligand is added stepwise in the first, second, third, fourth, and so on and so forth steps. So at the end we will going to get ML minus 1 plus L to get MLN. So here the equilibrium constant Kn is called as Kn is equal to MLN divided by MLN minus 1 into L. So all these are, that is, equilibrium constant in the first step, second step, third step, and n minus 1th step, and lastly nth step here. All these are called as equilibrium constants K1, K2, K3, etc. Kn. These are all called as stepwise stability constants in each case by the addition of one ligand in each step. And the formation constant of the complex MLN may also be expressed by the following steps and equilibrium constants. Here ML gives rise to ML beta 1 is the equilibrium constant here, that is given by ML divided by M into L. And in the second step, M plus 2L gives ML2 beta 2 is the equilibrium constant, that is equal to ML2 divided by M into L to the power 2. Similarly, M plus NL beta N is the equilibrium constant, gives rise to MLN, and beta N is equal to MLN divided by M into L to the power N. So these are equilibrium constants, and this equilibrium constant is called as overall formation or overall stability constant. So now what is the difference here in the stepwise and overall equilibrium constant or formation constant? In the stepwise equilibrium constant or formation constant, that one ligand is added at a time. So here the total number of ligands are added to the metal ion at a time, that is M plus NL in the overall formation constant. So that is equilibrium constants beta 1, beta 2, beta 3 are called overall formation constants or overall stability constants. N is called as nth overall formation constant or overall stability constant. The higher the value of stability constant for a complex ion, the greater will be the stability. Alternatively, 1 divided by k values sometimes are called instability constants. That is, reciprocal of stability constants are called as instability constants. Now let us see what are the factors that affect the stability of metal complexes. First, let us see what is the effect of nature of central metal ion on the stability of complex, and that is stability of the coordination compounds. In case of the central metal ion, we have to consider the charge on the metal ion. In metal cations, higher oxidation states forms more stable complexes than oxidation states with ligands such as neutral molecules like ammonia, water, etc. There are few exceptions also, like carbonyl ligands, which form more stable complexes with lower oxidation state of metals. Generally, the central metal ion with higher oxidation state forms more stable complex. Second one, size of the central metal ion. The stability of metal complexes increases with the decrease in the size of metal ion. Generally, if you look at the size of the central metal ion, when it is decreased, then it will strongly held with the ligands and form a stable complex. So here you can see that the size from here to here it is decreased. So therefore you can see that here it will form more stable complex when compared to here. Then the second factor is nature of ligands. So the basic character of ligands is important here. Greater the basic character of ligand, greater is the stability of the complex. So it should be able to donate electron pairs. So more the ability to donate electron pair, then it will form more stable complex. In the 3D series metal ion, order of stability of the complexes with ammonia, water, fluoride, etc. If you look at, ammonia forms a stable complex than water than fluoride ion, because ammonia has more tendency to donate electron pair because it is more basic, hence it forms a stable complex. The nature of metal ligand bond also affects the stability of metal complexes. Higher the covalent character, the greater will be the stability of complex. For example, the stabilities of silver complexes have different halide ligands which are in the following order: AgI2, AgBr2, AgCl2 and AgF2. Now, the ligands having vacant p or d orbitals tend to form pi bond, and hence they form stable complexes with the metals. Ligands that are capable of forming such pi bonds are CO, Cn-, alkene and phenanthroline, etc. The third effect on the stability of complexes is the chelate effect. That is, chelating ligands are molecules which can bind to single metal ion through several bonds and are also called as multidentate ligands. The metal complexes formed by chelating ligands are thermodynamically more stable than the complexes formed by the monodentate ligand. So there are a few examples which I have given here. That is ethylene diamine, triethylene diamine, etc. The next effect is macrocyclic effect. A macrocyclic ligand is a cyclic molecule that contains 9 or more atoms in the cyclic structure and has 3 or more potential donor atoms which can coordinate to the central metal ion. So, macrocyclic ligand is a cyclic molecule that contains 9 or more more atoms in the cyclic structure and has 3 or more potential donor atoms which can coordinate to the central metal ion. It has been observed that the stability of metal complexes in the presence of macrocyclic ligand of appropriate size is higher than the stability of complexes coordinated to open-ended multidentate chelating ligands. So few examples includes the Crown ethers and heme as ligands. The overall session summary is like this. The stability constant, that is formation constant or binding constant, is the equilibrium constant for the formation of complex in the solution. Formation of a complex MLN in solution proceeds by the stepwise addition of ligands to the metal ion in getting the stepwise equilibrium constant or formation constant. And the nature of metal ion, nature of ligands, chelation and macrocyclic ligands are the factors that influences the stability of the complexes. Let us look at a few multiple choice questions here for your reference. First question, a stability constant is dash. Options are numeric constant, real constant, integer constant and equilibrium constant. We have seen that it is the equilibrium constant. And the second question is, higher the oxidation state forms dash complex. Options are neutral, less stable, more stable, none of the above. So you can see it forms more stable complex. And the third question is, chelating ligands are molecules which can bind to single metal ion through dash. Options: 1 bond, several bonds, 2 bonds, 3 bonds. It may be several bonds. And the stability of the complexes here for these complexes with the chelating ligands are of the order option A, B, C and D is none of the above. So the correct answer is option A, because the chelation in this case is more and hence it will form a stable complex when compared to this. So you can go through these textbooks, that is Advanced Inorganic Chemistry by Cotton and Wilkinson, Principles of Inorganic Chemistry by Puri Sharma and Kalia, Introduction to Coordination Chemistry by Jeffrey Lawrence, and Modern Aspects of Inorganic Chemistry by Emilius and Sharp. Thank you very much for watching this video.